All right, I did several things this week, but I guess the biggest one is I decided to. So last time I said I was gonna try to optimize the program that reads the log file and generates the past dates into a history file, right? Um,
Yeah.
so that program is written in Python, and I said in order to optimize it, I said my hypothesis is that um, there's a lot of data duplication whenever I have like a dictionary and when the program is making updates to that dictionary, there's data duplication because it's having to reserialize all the fields of the dictionary,
Yes.
all the entries of the dictionary every time, and then resaving that and all the values every single time there's an update to that dictionary. And
Yes.
my strategy was to not do that anymore and instead have every single field be a pointer to another value so
Hmm.
that when a value changes, it's only updating that value. And then the pointer still doesn't have to change, is because it's just pointing to the value that is going to change, right?
Hmm.
Um, so I I implemented that idea partially. Yeah,
Uh-huh.
I implemented it enough to be able to do that process with some smaller programs, like or just subset of the whole Python language.
Hmm.
Um, I got it to work for dictionaries and a little bit with lists, but I
Hmm.
don't have everything working yet. But
Hmm.
because I'm impatient, instead of getting everything to work first before doing the performance comparison, I did the comparison, you know, the first chance I get. So
Hmm.
so I did some performance comparison, and oh, kind of want to show you to compare. Give me 1 second.
Okay.
Okay, so first of all, I want to talk something about performance tuning in general, like maybe make it a little bit instructive, even though this is like a sort of like a case study where we're talking about this specific instance.
Hmm.
um, I still want to try to give some takeaways that I learned
Hmm.
while doing this. um, so one of them is sort of using a profiler, which is there's pros and cons to doing this approach. But basically, so if I run, so I have this recreate command, which I could run using Python 3. Let's say I do it on, so this dot rewind file, that's the log file, and then recreate is gonna sort of recreate the past states. And at the moment, it's kind of slow. Okay, I'm gonna, I think the Fibonacci program is kind of, oh, there's the Fibonacci program. Okay, I'm gonna make it do a smaller number, so this will not take as long. um, so
Okay.
I was making it a lot to test the performance. Okay, so now it'll complete immediately because it's doing much less stuff. Maybe I'll make it a little bit more. Okay. Okay, that took like maybe a second or so.
Hmm.
Um, so there's a Python profiler that you can use, which you do it like this. C profile. I think you set a sorting option, and one of the sorting option is cumulative. time, cumulative CUM time, which stands for cumulative time. And it gives you this table. And what this table is, first of all, it gives you the total time of the program, the total time that the program took. And then it gives you, for each function that it traced, some statistics. And this graph or this table is sometimes hard to make sense of. There's a lot of data, and the key that the thing you're trying to achieve is to make sense of how the data relates to your program's performance. But basically, for each function, well, each line is a function, and if the function is module, that just means my entire Python file, my recreate.python file. So my entire Python file has these characters, has these numbers associated with them. What do the numbers mean? The numbers, this cumulative time means the total time it took between the start of the program and the end of the program. This tot time, total time, is actually means the cumulative time minus the cumulative time of all of my children function calls. So basically, I have my cumulative time, and then I will take the cumulative time of each of my children, add them together, and then I'm going to subtract that away from my cumulative time. And that's my total time spent within my function, kind of. Does that make sense?
Sort of. It's kind of like the Chrome debugger-ish.
Yeah, Chrome debugger.
Well, it's the Chrome profiler.
Chrome profiler, yeah. Chrome also has a profiler. Yes, that has the same kind of thing.
The children, and it has the children, kind of.
Yep. Oh, this doesn't have a tree form. I believe that one has a tree form, which I think is more useful probably. But I haven't used the Chrome profiler in a while. I don't remember what that looks like exactly. But anyway, what I did with this is, like previously, I thought that like what I needed to optimize was that data aspect. And after studying this a little more, I realized that was not true. And I'll show you what I mean. So first of all, in order to read this a little bit easier, I actually sort of refactored my code a little bit. Oh, I'll show this one. So first, I wanted to know the difference between, like, I wanted to know whether it was the parsing code that was slow, or the other code that was processing the thing that was slow. So I extracted. I already had a parse line function, but I extracted another function called process command. And then that way I have like a clear separation of these two responsibilities. And I was assuming that these two were completely non-overlapping and independent. So it turned out that was not true, but it's a good enough approximation. So then I can see, oh, well, parse line took this amount of time, whereas process command took this amount of time. So 0.727, and then if we divide it by the total time, which I'm gonna take from here, 1.439. That means the process command is taking about 50% of the time, and then the parse line is not much different. It's about 50-50, right?
Yeah.
And And so I did this kind of analysis, and if I wanted to break things down further under process command, then I take a look at all the functions that process command calls, and
Uh-huh.
then sort of do that kind of calculation. And I sort of did that. So like process command calls process call start, for example, some of the time, and it calls process push frame some of the time, and then I can sort of tally up these times and build a graph, which I did. For
Oh,
one of the cases, I made a graph. Let me see if I can find it. Yeah, this one. So I
oh,
made this. I took the data and put it into this spreadsheet,
uh-huh.
and I put in a couple of formulas to total the numbers, and I
Uh-huh.
think I made a graph. There's the graph. It's still loading.
Uh-huh.
Yeah, so that's the graph, and so that's an example of the type of thing that you can do to try to analyze this data. But this is saying out of all the things that it's doing inside of process command dispatches the control to one of these functions over here, and then this is the distribution of the total time of those child functions.
Okay.
And we can see that process call start takes the longest time out of all of them. And it takes about 20% of them, and so forth. Um, but later on, I realized that process command actually has one part in it that calls parse line,
Mm-hmm.
which makes it slightly overlapping. So
Okay.
these so my numbers actually turned out to be slightly misleading.
Okay.
um, so that's the kind of thing you have to watch out for when you're doing this, and I think that's actually a disadvantage of like a table like this, where it's all tallied based on the function in a flat way instead of a hierarchical tree way.
Yeah.
So
Okay.
because you now you could have overlaps, like if this function gets called by, like in my case, it's like some of the commands, like process call start actually calls into parse line, which
Mm-hmm.
is the thing I was trying to separate out. Now, now I have to do some extra work if I want to really separate them out. Maybe have a separate function called parse line A versus parse line B, and
Uh,
then have this one only call that, and then keep them separate.
yep.
Um, but
How
this sort of a hint at like there might be a better way to visualize this data. So
uh-huh.
like those are things that we can potentially think about later on.
Well, I
We're
like
thinking
promise.
about using the debugger for performance profiling stuff. Um, but anyway, I'll give you the sort of the conclusion that I came to
Okay.
after looking at the data in a more rigorous way than I had before. So
Uh,
basically, I had a run where I ran this profiler, ran my new version of Recreate, which I call that Recreate 2.
okay.
I ran that and I compared the result to the Recreate 1. Um, and I ran it on a relatively large log file. And I realized that, first of all, the total performance, like I did it with the Fibonacci, I'll call it Fib, and I ran it for when it tried to calculate the Fibonacci number at index 20.
Okay.
And then it was like recreate.py took 9.141 seconds, recreate2.py took 8.099 seconds. So it was slightly faster, but not fast enough that it's definitively faster.
Mm-hmm.
Um, and then under there, I found that parse line, the parse line is usually it's the entry point for the parser. So parsing each line of the log file. And then process command is after you parse the line, now you're gonna process the thing, do stuff with data structures and save it into the database.
Mm-hmm.
So in the old one, it was, those numbers, and in the new one, is in the new one it was these numbers. So so you can see that it's like 50-50, where about 50-50, but the parsing is actually slightly worse than the processing in both cases. In the new one, the processing is slightly better than the old one, and that could be attributed to the new scheme that I'm using.
Right.
But it wasn't a huge difference, and also one of the things that this execute is like the database call. The total of the time that's spent like interacting with the database, the SQL API, SQLite API, is that amount in the old one. Whereas in the new one, it was that. There's actually, it's even slightly worse than the old one. So there isn't like a, there isn't a clear improvement in terms of the amount of time dealing with the database. However, when it came to serializing, the old one had some time dedicated to serializing the data before the data goes into the database.
Right.
Whereas in the new version, there was no serialization needed. So the new version has zero serialization overhead. But other, like you can see that the other part is actually 2.6. Like if I subtract that number from that number, we get that number. And then over here, if I subtract these two numbers from this number, I get that number, which shows that this other than the stuff dealing with this inserting data into the database, there's still a significant amount of work outside of that.
Yeah.
So my scheme, my new data scheme was targeted at specifically these two things. However, that's not necessarily a huge portion of the overall process.
Yeah, that makes sense.
And in a way, I have eliminated this serialized part, but that serialized part is, if I divide it by the entire thing, which is 9 seconds, that's only 11% of the big picture. And yeah, maybe I have done something, but it's clearly not a huge amount
That's
to the overall performance. So another thing is I made a code example where that clearly favors my new approach, which is it creates a enormous dictionary. It's like of like 10,000 entries in the dictionary. So that's gonna clearly favor mine. And when I did that, what I found was that, see, I'll call that the big big dictionary. When I did that, yeah, the with a big dictionary example, the old one took 7.071 seconds, and the new one took 0.513 seconds. So there's a huge difference if I have a enormous dictionary in the program. Then mine is much better.
That makes
But if we can drill down into the specifics to see where all of that time is being spent. So in process command, it was 6.570. So most of the time was being spent in process command in this case now, whereas the parse line only took 0.286 seconds in this one. So when it's really bad for the old old data scheme, it was because the process command part was getting really bad. And more specifically, it was the serialization part that was getting really bad. Most of the time was spent in the serialization. And this is actually 89% of the total. So what I'm saying is, if there's a situation like that clearly favors the new scheme that I worked on, then that will be because the old version of the code is doing way too much serialization.
sense.
But then I also had to ask, like, in the practical cases that I have encountered, like, because when I'm trying to optimize, I'm trying to optimize for my own workflow and like actual scenarios that I encounter that are slow. So I chose some of those that I encountered that are slow. One of them was the Fibonacci one, but another one is I tried to have the recreate script generate the past states for itself. So I had create the log for read the recreate log back in. And when I did that, I found that more or less still the parsing was about 50-50 with the process command, which shows me it's not a case of it's doing way too much serialization in that case, in the practical case. Even though generate a case that's really bad for it, practically I haven't hit those cases yet. So that one was like when I have recreate running the recreate rewind file, I got the total time to be 33 seconds. And the parse line time was 15 seconds. And the process command time was 17.229 seconds. I didn't do this one with the new version of Recreate because it's not there yet in terms of features to be able to do this one. But and then if we break it down a little bit more, inside of process command, the db execute took 6.222 seconds, and the serialize took 3.752 seconds. And then other than that, it took 7.255 seconds. So currently, the serialize is there's some amount of serialization, but it's still not a huge portion of the overall picture. Like the other is even greater than serialize. And then so when I ask the question, like, what is all this stuff in other? What are you doing other than inserting data into the database and serializing the string? the only answer I could
Right.
come up with was just that it's just doing the like doing stuff with dictionaries, doing stuff with lists, if statements, like all the normal things you do with the programming language, right? Like these are
Mhm.
just like core features kind of Python.
Oh,
So that's the point where I said, okay, it's time to rewrite this in C because
okay.
because it's so because if I look at this big picture, it's like this time because my initial theory was, hey, it's the database that's slow. It's usually the database that's slow. When you're optimizing things, usually the database is the slowest thing, so you have to optimize the database. But in this case, it's actually not, because if you take that number, okay, there's a little bit more, because other than the database execute, there's also a commit call
Mm-hmm.
that uh, that's outside of parse line that is taking that amount of time. So, but if I but that's insignificant. So if I take that and divide it by the total number,
Mm-hmm.
it's 20% of the overall time is being spent dealing with the database. It's only 20%. The
Yeah.
other 80% is not database at all. That's just Python.
Okay.
So
So
basically, I decided to rewrite this thing in C to
okay.
get maximum performance out of it. And
So why C is much faster than Python in this case?
yeah, that's a good question. Why is C much faster than Python? So um, Python is an interpreted language, and I actually have gone to take a peek at what the interpreter does. But essentially, it's almost like um, there's an extra level of like you have CPU has instructions. CPU has instructions that looks like you put your code in here, and each line it's some bits that represent an instruction telling the CPU what to do.
Right.
Um, Python has a virtual machine, so these are instructions. Uh, but Python has a virtual machine. We call it the Python interpreter. Python interpreter is acting like a CPU, and it's reading in line by line. And then it has to look at the bits to determine what instruction this is, whether this is an add or load an object or initialize an object or call a method or whatever. And then it'll do the work.
Okay.
Um, there's a so each of these things, these actions that it does, like, hey, what is this instruction? Oh, it wants me to make a method call. Now I need to fetch the object that contains the method. Now I
Mhm.
need to load the method based on the method name. I I need to, based on the method name, I need to look up what the method object is. Oh, now I have the method object. I'm going to put the method object onto the stack, and then so that there's a separate instruction after that to actually call the method. And when I actually call the method, I have to take the arguments off of the stack and pass it into the method object in order to call it. So there's actually a whole bunch of sort of infrastructure level code that's going on. That's just making the language itself work. It's
Mhm.
just a lot of overhead. It's
Okay.
like you have to get through all the machinery it takes to just to do a method call
Mhm.
before the stuff that the method does actually even happens. And
Okay.
that's actually a substantial amount of overhead.
Mhm.
Whereas if you compile it in
That makes
C, the code in C just gets compiled down to the instruction sets that are fed directly into the CPU. And there's no infrastructure overhead involved at all. It's just doing what your program is trying to do.
mm-hmm. Gotcha.
Yep. So that's a short explanation. Um, but basically, what I did so far, which is very promising, is I wrote just the parse line part. I did an experiment where I wrote the parser in C,
Okay.
and then I tested that head to head against Python. So it's like
Uh,
C doing just the parsing versus Python doing just the parsing.
okay.
And the end result was like the C was 34 times faster.
Oh wow, that's crazy.
um, so and that is like very very like a lot faster.
Uh,
There's multiple reasons to why it like in Python I was also using the eval function, which was
oh,
slow, and there are ways I can do without calling the eval function to
mhm.
make it much faster. But other than that, it was just Python itself is slow.
Okay.
But yeah, by rewriting just the parsing in C, I got it to be much faster. And when I did some rough calculation, like if I can make this number like 34% faster, and if I assume that I assume the DB execution part, that's the part I cannot improve that much because it's calling into the SQLite API. And the
Mhm.
performance of that is determined by what the SQLite API is doing, right?
Mhm.
So I'm gonna assume this stays fixed, but I'm gonna assume the part that is Python code executing. I'm gonna assume I can get it to maybe around that number. I'm just gonna call it like one order of magnitude faster.
Okay.
Have you heard of this term before?
No.
Magnitude. One order of magnitude faster. Um, and which usually means it's 10 times faster. It's
Oh,
like
okay.
it's one power faster. It's like whatever the number is, x of n, we just we just like decrease this n by one.
Okay. That's
And
pretty.
34 is around there. I decrease this exponent by n. That's how much faster I made it.
Yeah, and you can also like make this other part in the process command faster, right? Like
Exactly. That's what I'm banking on, right? I'm as like first of all, the serialize part I can probably exit out if I use the new approach. There's
right.
no more serialize. And then but this other part, I'm betting that I can do one order of magnitude faster for this number as well.
Yeah.
So if that did happen, it would end up be like, well, as I calculated, I think the database, oops, I think the total database for this particular scenario, the total database time is 7 seconds.
Mm-hmm.
Um, and then that means the part that's not database time and is Python is 26 seconds. What if I
Mm-hmm.
can, what if I, all of that can be 34 times faster? That means all of that will now be 0.7 seconds.
Mm-hmm.
And then so if I can do that, I add that back to my database time of 7 seconds. The overall time will be reduced from 33 seconds to around 8 seconds. And
Mm-hmm.
that's a huge improvement, right?
Yeah, that's significant. Yeah, for
Yep.
sure.
So that's what I'm banking on. But there's a bunch of work to do, like to port
Mhm.
everything over from Python to be rewritten in C. So I'm working on that right now.
Gotcha. Well, that's really cool. Yeah, I think that's a great discovery for sure.
Yeah, I guess like if I were to try to summarize what I learned in this story, it would be um one of them is just like look for improvements by one order of magnitude. Like look, you know, like look for 10 times improvements, or one order of magnitude.
Mm.
Like don't try so hard. Don't try so hard to work on things that'll give you like 50% improvement. Those are not as meaningful. You really want to find something that gives you 10 times better or 50 times better or something like that.
Yeah. And you found a bottleneck. Well, but I guess in this case, like there is not like just one like a bottleneck that's very obvious.
Yeah,
But I
it's
guess
actually
because
just Python is slow. And but I
yeah.
had to do some deductive reasoning. Like, well, first of all, I had to visualize the results of the profiler, which
Mm,
was not easy. Like,
yeah.
I didn't get it the first time I looked at that data, but I tried to, I had to look at that data in a different way before I came to that conclusion.
Mm-hmm.
Um,
Yeah.
but but yeah, but I concluded that it was the Python that was slow.
Oh,
um, yeah, but you need to, like, you really want to understand what's going on. Like, the
mm-hmm.
more you understand, the more you understand what all the code is doing, the better. Um, and because and another thing I would say, it's like performance, getting code to run fast is not like it's not like running fast. It's not like Usain Bolt running super fast
Oh,
because he's just more powerful runner than every. It's not about power. Making code run fast is more about being extremely stingy with your resources,
mm-hmm.
if that makes sense. It's like the accountant that tries to cut expenses in all possible places. That's what it's more like.
Okay.
So you have to understand, like, it's like cost cutting. It's like it's more like cost cutting accountant, not not Usain Bolt. Like you're trying to figure out, oh, there's all this code that was executed.
Mm-hmm.
Which parts can I cut out?
Mm-hmm.
You look at, like, oh, there's a lot of code that's spent doing this thing. Can I cut that out? Um, and the only way you can know what you can cut out and what you cannot cut out is by understanding the code more, and then also look for, do the pieces that has the most value, right? Like you don't spend a lot of time cutting out the small stuff. You want to
Mm-hmm.
spend time cutting out the really big stuff to make a huge impact.
Yeah, that makes sense.